Good, this will make me even louder. All right, so let's begin the afternoon session. So we're welcoming a couple new lectures this afternoon. So first we're very happy to have Patrick Meade from Stony Brook University. He's an expert on all kinds of things, theoretical and phenomenological, but I think in particular, things like muon colliders, and he's here to tell us about future accelerators. So with that, I'll let him begin, please.
Okay, can you hear me better now? You probably heard me about the same, but yeah. Okay, so I'm very pleased to be back at TASI in this much fancier place than when I had TASI. I came here first as a student in 2004. It was the infamous year that when Fox News came because some hikers got lost with Tom. So it was not my fault, but I'm sure that's a story Tom has chastised every generation of TASI ever since then. And then I was happy to come back in 2009 as a lecturer, and we also didn't have this fancy room back then, but now we have a fancy room. So I'm talking about accelerating in the future. Jesse and Nathaniel like very whimsical sorts of titles for everything, so I don't know exactly what this means, so I'm taking my own spin on it. So what is my goal in 3 short lectures? My goal is, even though this is a theory institute, I'm going to try to give you an appreciation for accelerator physics, okay? It seems kind of a foreign concept. I mean, certainly when I was your age, I didn't care particularly about how you made an accelerator or how you put an accelerator together. But it's really actually important from the theory perspective as one of the main tools that we use in particle physics. And when we think about the future of particle physics, it's really crucial that everybody at least has some basic rudimentary working knowledge so that when you talk about the tools that you're going to use to write down your theories or interpret how the universe works, you need to have at least some sort of basic rudimentary language that you can tell whether an accelerator physicist or experimentalist is trying to BS you or not, right? Lots of people will say they have great technologies that are just around the corner, but of course, some of those great technologies have been just around the corner for 100 years or 50 years. So as theorists, we're the kind of glue that brings the entire field together in terms of what it is we want to be searching for, but we need to know what are the technologies that are realistic or not. Now, the next side of this is what is the current picture for future accelerator projects and current accelerator projects?
Yep. Tau-on collider.
It's an idea. We can talk about that more. One of the big parts of this is to think about in some of the proposed projects that are out there right now, we're kind of doing this transition period in the field. We've had a collider running for a long time at CERN. The entire field, Europe, China, North America, we're all thinking about what are the next big projects. So I want to kind of give you a feel for what it is that current status. And as Ethan said, I've spent a good amount of time thinking about muon colliders lately. And then last but not least, as a theorist, I mean, I'm not going to be able to give you the nitty-gritty details of all accelerator physics. What I really care about accelerators from the perspective are, what are the physics questions that we can answer with them, okay? So I'm going to try to give you a whirlwind view of this in 3 lectures. How much you actually get out of it, we'll see in the next 3 days. So as a first icebreaker, so the first lecture's already written, second lecture's there, third lecture's sketched. I want to kind of get a feeling for how to maximize this for all of you. So as an icebreaker, since Nathaniel didn't tell me exactly the breakdown of the TASI students, raise your hand if you've ever done a collider pheno project, written a paper on it. Okay. So that's actually a good fraction of you, a higher fraction than Nathaniel suggested. So some of you might be very bored today. Nevertheless, it gives us a picture. And for those of you who haven't, and even those of you who have, one question that we can go through to kind of get everybody participating at some level is I'd like to see how familiar you are with many different accelerators we've had over the last almost 100 years. So let's start off. We'll raise hands based on the colliders you've heard of. So let me write a few of these. So let me do the verses. Has anyone not heard of the LHC? Okay, that's obvious. Okay, the problem, those colliders are around for a long time. So all of a sudden, you can go back a decade, and I mean, looking at the age of this audience, run out of colliders very fast. So the next one, is anyone not familiar with the Tevatron? Okay. Yeah, I mean, you went there. Okay, good. We're on a good start. How about LEP? Anybody not familiar with LEP? Okay, well, it's perfectly fine. I mean, no harm in this at all. Next one we'll go through, SLC. Okay, now we're starting to get to that age bracket where this is less familiar with. So this was the Stanford Linear Collider. This is what the kind of cornerstone of SLAC was. Yeah. Yeah, SLC is the collider. SLD was the experiment. SLAC used to be the Stanford Linear Accelerator Center. And then that wasn't the main thing, and they didn't have that, so SLAC is no longer an acronym. It's just SLAC. That's how the DOE does things. Okay, so now we've kind of gotten historically where we're becoming a little less familiar with this. We'll go even more. SPS. Okay, since I didn't dig, who's not familiar with SPS? Okay, more and more people. Okay, so this is the superproton synchrotron that was at CERN. It's also sometimes referred to as the SPB bar S, which is what discovered the W and Z bosons. Okay, so we're getting there. So now we've kind of got a rough age. Now I'm going to give you kind of two that are, well, one that's very obscure. We'll start with that. Isabel. Who's not familiar with it? Well, let's reverse it now. Who's familiar with Isabel, other than Tom? Okay, so Tom and I are the only people in the room that have heard of Isabel. This is unfortunately where we also get into.
Heard of is different from familiar.
There you go. I mean, we can judge it. I leave it on you how you decide to answer. Raise your hand. So Isabel, the reason why you probably haven't heard of it is this is in the graveyard of accelerators. This was a project that was tried to be constructed by the United States at Brookhaven National Lab. It was meant to compete and discover. Unfortunately, accelerator technology is very, very hard, okay? And Isabel was supposed to be a 200 GeV on 200 GeV, proton-proton collider at Brookhaven. They never could get the magnets to work, and funding, et cetera, there's many reasons this thing died off. The nice thing is they were able to reuse this. Isabel, the experimental halls and part of the tunnel were built. And how many of you have heard of Rick? Okay, starting to get the fraction back up again. Rick lives in the old Isabel experimental halls and tunnel. Okay. Now, for the one that brings the most angst to a certain generation of particle physicists, hopefully no angst to any of you, the SSC. Who has not heard of the SSC? Okay, so that's good. That's a very good thing. We're seeing turnover. This was supposed to be the mega project for the United States, the superconducting super collider. It, unfortunately, unlike Isabel, it didn't get reused. It just is possibly a mushroom farm now. You can ask Nathaniel Craig. He likes to go visit the old site in Texas for some reason, take pictures. He can show you pictures of this. This never actually existed. Now, I'll give two other old school ones just to kind of set the pace for this, and I'll show a picture of this later. The Globaltron. Who has heard of the Globaltron? I even got Tom on that one. Okay, I'm going to show a picture of this later. I'm not going to tell you what it is now, but I'm just kind of getting where the room's at. Now let's flip the script a little bit. These are all projects that either exist in the past, or were proposed in the past and never actually existed. The next version of it is thinking towards the future, okay? So let me get show of hands of how many people know what the ILC is. Okay, now we're starting to get back up on the train again. How about something with very similar letters, but a very different project? Click. Okay, everyone's there. The one that you probably have heard the most about, if you look in popular press, are two versions, FCC-EE and FCC-HH. Who has not heard of FCC? Okay, there's only a few of you. So that kind of resets the normalization for where we're understanding things. How about the analogous ones in China, CPC and SPPC? Who has not heard of these? Okay, so this is essentially the same as this, just in China. That's the thing we're going to go in more detail later. Okay, now the favorite one for me. Who has not heard of a muon collider? Okay, so everyone except for him is going to get a sticker when I come back tomorrow. Okay. Now, since I wanted to kind of get into the more obscure ones as well to see where the audience fell off, and I got Tom to fall off eventually with the Globotron, who has heard of the CQ proposal? Okay, so we got some people that have heard of CQ. That's great. How about Helen? Okay, now we got back down to 0 again. So this is, I'll tell you about that as well. Now I'll give the most obscure one. I was hoping to not get to 0 quite yet, but I need an eraser. This is, in some sense, the newest proposal on the block. But maybe somebody who has a certain German affinity will know this. HALHF. Has anyone heard of half? Okay. So this is the highly asymmetric linear Higgs factory that Daisy just proposed last year. Okay. Gotta love the acronyms. This actually, and we'll talk about the technologies involved in all these things more in tomorrow's class. This represents the first semi-realistic attempt to make a wake field collider. So wake field is a possibility for accelerating particles. The Daisy group would like to do this, and I'll tell you about it more later. Okay, so we've kind of got a baseline for what projects are. A lot of you are familiar with it, but we'll go in a lot more detail. Now, these are a number of different particle accelerator, particle collider projects in that we all just, as theorists, say, okay, that's great. Tell me what the parameters of these things are. Are you going to actually build it or not? And we'll do some calculations for it. But the other side to this is when we think about accelerator physics, we think of this in the context of building these big projects. But there's only a handful of projects written on the board. Okay? There's only a handful of particle colliders running in the entire world right now. But let me ask the reverse question for accelerator physics. How many particle accelerators do you think are operating in the world right now? Anybody want to venture a guess?
Thousands?
Thousands, that's a good guess.
Thousands.
Tens of thousands?
Millions. There are probably some medical devices everywhere that are doing
Okay. So tens of thousands actually turns out to be the correct answer. So the current estimate from the IAEA, the Atomic Energy Association, says there's roughly about 30,000 particle accelerators. Okay. So accelerator physics is actually a gigantic field, okay? And it's estimated that 97% of all particle accelerators have absolutely nothing to do with basic science, okay? So as one of the people pointed out, that one application for particle accelerators is medical science, okay? Both in terms of imaging and in terms of cancer treatment, okay? Both using electrons and protons for cancer treatment. There are lots of other kind of just applied versions of particle accelerators. So for everybody that likes computer chips, likes your semiconductors, okay? Well, we would like to dope these semiconductors to give them the properties that they want. So about 10,000 particle accelerators use something called ion implementation, where they use a particle accelerator to accelerate ions, and then they can control the depth that the ion will get deposited into your semiconductor, and you can change the energy levels, et cetera. Food sterilization. You can use this for materials science. One of the most quirky versions of what a particle accelerator is useful for is shrink wrap. Okay, you have to take your cling wrap, okay? Apparently, I don't know the chemistry of this sufficiently, but the polymers inside what you make shrink wrap for, by using electron accelerators to bombard that material, that changes the polymer binding structure, and that's why it has that funky ability to cling and to shape the way it does, okay? So particle accelerators are everywhere, okay? Particle physicists, we're the ones that created all this stuff, but now the rest of the world takes it, okay? The nice thing about this, though, is if you understand the interplay between these two things, we can also better connect with the larger public in terms of what the applications of all these things are, okay? So it's an important thing to keep in the back of our heads that particle accelerators, they're things like the LHC at CERN, but tens and tens of thousands of these things are not anywhere to do with something like Higgs physics or anything like that. Now, I had the fortune of always being at universities close to national laboratories, or when I was in grad school at Cornell, we actually had a particle accelerator on our campus. So the one thing I also didn't appreciate, though, as a grad student at your age in TASI, many of you probably have never even met an actual living accelerator physicist. Because even though lots of universities have theoretical physics programs, there are only a handful of accelerator PhD programs in the entire country, okay? Even though these are the people that are going to be responsible for making the experiments that you would like to eventually use in your lifetime, or having all this technological spin-off. So that's what I mean by I want to give you a sense of appreciation for accelerator physics. Okay, we haven't gotten to the questions it can answer, but it really is a gigantic field, and we need to understand the basic technologies that go into it. Now, of course, you're all theory students, and you probably really don't care exactly what an alternating gradient synchrotron actually looks like or things like that. What we care about are the physics questions we want to answer, okay? So before we go into the accelerator technology, I'm going to kind of circle back and talk about some of the physics questions and where do accelerators really fit into answering some of these questions. So we always start with things like big questions in HEP. And you're going to have lots of sets of different lectures, or you already had some, like Tien Tien came last week with dark matter. You'll hear Matthew call about change in paradigms. Everybody's going to give you a different kind of spin on these sorts of perspectives. And we can always do the same things that we do in every sort of talk like this. You say, what is dark matter? What is the nature of flavor? And neutrino mass. Did your neutrino talk start today or tomorrow or yesterday? Okay. So, or things like, why is electroweak symmetry broken? So you're going to get many, many questions and potential answers from a number of the lecturers. And what we'd like to do is try to take our theory brain that wants to answer these questions and try to figure out what's the best way to optimize the answer to a number of these questions. Now, for everybody that's here, this is ostensibly a more pheno year for TASI. But at the same time, all phenomenologists at some point have some fraction of their brain thinks of a hep-TH person as well. We kind of go back and forth, and where you actually sit in your mix depends on your individual preferences. Now, if I wasn't trying to think about experiments at all, there is kind of this basic premise that as theorists, we could hopefully figure out what the universe is just by reading the tea leaves of what we've already been told so far, okay? Now, this is definitely a powerful approach by trying to understand through consistency and symmetries what we can do. And it's given us a long path along the way where we can say, like, okay, once we figure out quantum mechanics, we can evolve to quantum field theory, and then maybe the next layer is string theory or something like that. Unfortunately, what tends to happen when we try to just think about this without the tools, the experimental tools, is yes, we can develop powerful, consistent frameworks, but at the same time, our frameworks don't tend to push us to a very unique answer in terms of what we want to look for experimentally, okay? So it would be really great that to answer this question, we knew exactly that theory dictated it had to be at X GeV or with this coupling or whatnot. But unfortunately, that's just not the way it works, okay? We haven't had any success along that way. Nevertheless, some questions will localize a bit in energy scales, and you'll hear about those. However, the other way to think about, in some sense, the space of all answers, and I saw in the first set of lectures on entering the subatomic realm.
Patrick?
Yep.
I might encourage you to use some of the other boards too.
Sure, yeah. Okay, now we'll break parity and come to this side. My apologies to that side. Okay, so what we can think of, though, a different way to parameterize the space of answers to BSM questions, which was already shown in one plot, is to think about what defines BSM states. Okay. And we can go to more and more levels of rigor about this, but the kind of more agnostic version, instead of thinking about the questions, is just to say, well, we have a characteristic mass scale. And if we're ever to probe it with any experiment, it has to have some coupling to us, okay? At worst, it could be gravitational. So you've already seen this plot, and it gets shown in all kind of summary plots all around the world. And the version of this is to think of this projecting onto some 2D plane where we think of the mass of the BSM states, and roughly I'll call this the coupling to the standard model, okay? Now, in a real model, we have more than this, but this gives you the rough picture that you already saw in the very first set of lectures. Now, the nice thing about this space and why people use it so often is that it is a bounded space, okay? In terms of the mass space, we can think of things that have no mass, and then, well, eventually, this, in terms of elementary particles, is cut off by roughly the Planck scale, okay? Similarly, the coupling strength, well, we can't go arbitrarily weakly coupled. We can think of this as gravitational coupling. But the other side is, through our framework of quantum field theory, we know that we don't have arbitrarily strongly coupled theories. We know we can think of this as a unitarity limit in terms of our quantum field theory description. Now, of course, we might have to switch to another description as we go here, and this plane might not be the right plane for that theory, but we can't just talk about couplings that are arbitrarily large in the context of quantum field theory. So from this perspective, instead of asking those specific questions and trying to be the best theorists we can and give us our best guesses, we would like to just hopefully cover this plane. And so we can imagine that the standard model lives somewhere in here, because it has its coupling to itself as well. And then the real question is, how do we cover this space? Is new physics here? Is new physics here? And we'd like to somehow map this entire space and then brute force. If we could do experiments to do all this, theorists don't have to be too clever. They just find the new physics. Now, why do I emphasize this particular perspective versus the questions I want to answer that are deeper? And we'll come back to those deeper questions. The real point is that if we were trying to cover this space, we need to understand what are the experimental tools that are available to us, okay? Because we have all different types of tools. It doesn't just have to be accelerator physics. But the important part is, even though we have many different tools, it's the theorists, all of us in this room, that have the underlying framework of quantum field theory plus general relativity that let us tell us how these different tools show up in different regions, okay? If there was some magical experiment that covered all of this, we wouldn't have to do this. But as theorists, we know how to go between these various tools. So I want to do one particular example of this to kind of show how accelerator and collider physics fits in compared to other things. So obviously, it's going to be very hard to get up to the Planck scale in terms of energy. Okay, we might do it one day. But one of the techniques we can do is to compare, instead of direct probes of high energy, we often do precision experiments. Okay? And now the nice thing is, as you already heard also in the first set of lectures, if I can't probe, for instance, a point at very high mass compared to the characteristic scale of the standard model, order 100 GeV or so, what I can do is I can understand how this UV physics maps down to low energies. And again, we have the framework of effective field theories that lets us talk about just using the degrees of freedom of the standard model to probe very high scales. So let's take one particular example of how we can use effective field theory techniques to talk about very low energy processes and see where do they actually probe in this scale. So an example of what would be a great probe to go to very high energies would be, for instance, to use cosmology or astrophysics to probe this. Okay? So cosmology and astrophysics have a great track record of doing things that we can't do in terms of terrestrial experiments, like dark matter, dark energy, hints of that inflation's the right theory from the early universe. The problem is these give us hints, but we don't know exactly where they fit on this plane, right? Inflation could happen within roughly 14 orders of magnitude or so. We all believe inflation happened, but we don't know where it sits. So there's lots of great examples of cosmology and astrophysics leading us in the right directions, but we don't know exactly where to put this in. But of course, sometimes it can get even more specific. So something that happened well before all of you were born, even before I was born, is the famous solar neutrino problem. So the idea being that if you really know what's happening out there in the rest of the universe, like if you have a great solar model, you can make predictions for where things happen. And you can then say, okay, if I trust this enough, I can find that, oh, maybe there should have been neutrino mass and Bacall should have won the Nobel Prize. However, for every kind of indirect hint, we always have the problem that if we can't actually do it in a lab, it's hard to reproduce things, and so there's a lot of inference that has to go on, okay? So even if we can discover things astrophysically, we still might want to have some sort of probe in everyday life. So for instance, since your neutrino lecture just finished, we're still trying to understand what the nature of neutrinos are, and one of the major accelerator projects in the US right now is the DUNE experiment, okay? Now, this is certainly, astrophysics cosmology is a great way to attack this kind of plane of not knowing what the answers are. But what we'd really like to do is understand also what are the types of experiments that fit in when we talk about experiments we can do on a tabletop, right? If you don't want to build a 27-kilometer ring at CERN, if you don't want to just hope you understand how the universe evolves or how certain stars evolve, what you'd love to do is build a tabletop experiment. So I want to give an example of this, which using EFT techniques, which is the electric dipole moment of the electron. Okay. So this is something that's yet to be observed, okay? But maybe the electron has a tiny little dipole. And you can build tabletop experiments, tabletop in the sense of you can fit it in a lab in some basement, okay? And the current best constraint on this comes from the ACME and the ACME 2 experiments. And what they set is that there's a current limit on the electric dipole moment of the electron that's roughly 1.1 times 10 to the minus 29 electric charge times centimeter at the 90% confidence level. Okay? So I'm sure Yuri Zupan in his talks on precision will talk about experiments like this in a lot more detail later. But for my purposes, I'm going to focus on where does this leave us in a plane of not knowing what the couplings are, not knowing what the mass scales are, okay? Now, the question is this an important number or not, okay? Now, we haven't seen electric dipole moment, so 10 to the minus 29 centimeters sounds like a very nice number. I mean, lots of people are caring about this, but where does this actually fit in the coupling versus mass plane? So the 0th order question we could ask is, does the standard model predict this process at all? Okay, sometimes we're searching for processes that are absolutely forbidden in the standard model. Sometimes we're searching for processes that are just really, really tiny. Now, there can be various contributions to electric dipole moment in the standard model. This is, if it exists, it's something that violates CP. So there are sources of CP violation in the standard model, okay? There is the CKM phase in the quark mass matrix, okay? But it doesn't talk to the electron directly, so we have to get there from the CKM phase to the EDM of the electron, okay? There also could be other sources of CP violation in the standard model. For instance, say if we ever measure non-zero theta QCD, okay? That would also have to go from the gluon operator to the electron, or an association with neutrino mass, we could have phases associated with neutrino masses. Okay? Since we haven't observed a non-zero theta angle, and we haven't observed CP violation in the neutrino sector, let's just stick with the standard model for a second. So the CKM phase is the only thing that's definitely there. And then we'd like to ask, well, if I take my theta CKM, which lives in the quark mass matrix, how does that actually show up in an electron EDM? Well, it turns out that even though naively we're just saying, oh, I just need to talk from quarks to leptons, the weak force lets us talk between quarks and leptons all the time, that mediates this. The problem is it doesn't show up until much higher order, okay? So it certainly can't show up at tree level, because to generate something that generates CP violation, I need something that gives me an imaginary component. If I took something at tree level in the standard model, it had a phase, just tree level, it would be diagonal, and then I would have a real component. So it needs to at least occur at beyond tree level. Now, if I go to loop level, the question is, at what order in loop level does it occur in the standard model? And it turns out that the EDM, what I have to do is somehow go from the quark sector to the electron. So I can think of first asking, how do I generate an EDM for a quark? Okay. Well, if I want to generate an EDM for a quark, and I want it to be proportional to theta CKM, okay, the funny part about flavor physics, that I'm sure Yuri will talk about more, is that you have this ability to rephase all the quarks. You can always move things around. Okay, that's how we get the CKM matrix. So it turns out that the only way to actually say definitively that it is an EDM for a quark, not just a generic thing, is there's something called the Yarlskog invariant, which is the rephasing invariant to say whether you have CP violation or not, okay? So it can't be tree level, it has to be loop level. It turns out that if I go one loop, it doesn't work. Two loop, it doesn't work. And then the reason why is that this Yarlskog invariant, okay, which I'm not going to go into for lack of time, but hopefully Yuri will, this is anti-symmetric amongst all the flavors of the standard model. So you need to touch every single generation. So it turns out that a quark EDM first shows up at 3 loops in the standard model. Okay? And then, if you wanted to show up into an electron EDM, which is the best measured thing, we now have to take that quark EDM, attach it to an electron through another loop, and you get the infamous diagram that someone's probably drawn at some point for you in your life, where you take a quark loop, you have a W, you have to have a gluon for the right antisymmetry in terms of the color and flavor, you attach 2 Ws, and then you have a photon coming off. Okay, I'm sorry that the board technique didn't work that well there. But this first shows up at 1, 2, 3, 4 loops. Okay. So the question is, what is the actual prediction compared to this great number that the Acme collaborations of 10 to the minus 29 have come up with? And the answer is that the prediction, based on the 4-loop result, put it up here, is that the electron dipole moment has to be about 10 to the minus, I'll put greater than 10 to the minus 44 e centimeters. Okay. It could be bigger than that if we have a non-zero theta QCD or neutrinos, but just using the CKM phase, we're still many orders of magnitude compared to what the experiments are at. But it still sounds like a really great number to say, hey, I've got 10 to the minus 29. What does that imply in terms of this coupling and mass space here? So let me leave this coupling and mass space up here, and we'll just do a calculation for understanding where does this point map to. So from an E of t point of view, if there's something beyond the standard model that gives an electron dipole moment, well, we can represent this by a dimension 6 operator in the standard model effective field theory. And the operator that does this is an operator that looks like the following. I, H dagger, we have our lepton doublet, sigma mu nu, then we have our right-handed electron, and then I can have either a B mu nu or a W mu nu. So this is the dimension 6 operator that can generate an electron dipole moment. Okay? Now, the question though is, how do we convert that experimental number to a scale associated with this EDM? Yep.
Why is the E bar on the right of the equation? Is it usually the bar thing on the left?
I mean, it's a matter of convention in terms of how you set up your standard model with your left-hand and right-hand fields. But
What if it was like a row vector, the other like column?
you shouldn't think of them as row and column vectors. You should just think of in terms of the representations of the Lorentz group that you're contracting in an appropriate way. Like in terms of if I have this thing it's contracting with the sigma matrix, but we can go through in detail. I didn't set up what the exact standard model and conventions for my SU2 cross SU2 was. But in terms of it's something that looks like a Yukawa coupling, but contracted with sigma mu nu with a field string. Okay. That's all you have to think of for this. Now, I'm not going to talk about any new physics that causes this sort of operator, but we know that this thing has mass dimension 6, so naively it's suppressed by some scale 1 over lambda squared. Okay? Now, the question is, how do we turn that EDM number that has been bounded by Acme, sorry, that's less than that because they haven't measured that, into this? Well, if I look at this operator and I compare that, that only has 1 power of dimension. And so where I get the extra power is from the Higgs, in terms of veving this Higgs. So what I really think of this is that the contribution to the EDM should look like some vev of the Higgs over some mass squared of some new particle. Now, if I play this game in terms of what does this correspond to, well, this needs to be about 10 to the minus 29 ECM. Okay, I bring down this board and we'll keep going. And now I just need to convert from centimeters to our mass scaled units of TeV or GeV, like we love to figure out where it fits in. So if I do this, so a centimeter is 10 to the 17th centimeter TeV inverse. So this gives me 10 to the minus 12 TeV inverse. Okay. Now, the vev of the Higgs is 10 to the minus 1 TeV. So what I have is something that looks like 10 to the minus 1 in terms of mass measured in TeV units. And then I have my 1 over the mass square. So I got 10 to the minus 12, I got 10 to the minus 1. So this thing needs to give me roughly 10 to the minus 11. Okay? So in other words, this sets some gargantuan mass scale of roughly 10 to the 5 to 10 to the 6 TeV. Everything is order of magnitudes. I've thrown away all other factors. Doesn't matter at this point here. This seems absolutely ridiculous that probing an EDM, which is many orders of magnitude away from even the standard model, is already probing this astronomical scale. Okay? Now, this estimate was done a little too fast because, as I said, this basic EDM operator for the electron, this looks like the Yukawa coupling for the electron. Okay? So if I was to have this operator turn on, the only difference between a higher dimensional contribution to the electron Yukawa versus adding a field strength for the photon or for the W's and Z's is sticking on this gamma or photon or W. Okay? What that means is that any new physics that we're generating in electron EDM should naturally also generate a huge deviation in electron Yukawa. Okay? So if I don't want to have this thing be parametrically changing what the value of the electron Yukawa is and fine-tuning it to keep the electron Yukawa fine but the EDM not being fine, is what I should think about, instead of parametrizing this by the VEV of the Higgs, which is there, I should think that a better estimate is to assume that this thing has to scale like the electron mass over m squared. Okay? This is not a hard and fast rule. This is just a Spurian analysis to say, I don't want to screw up the electron Yukawa, so rather than having an order 1 Yukawa, I should have something that's order the mass of the electron. And now we'd find that, well, this thing is going to be about 0.5 times 10 to the minus 6 TeV over m, and I still have my 1 over m. And now we'll go from the scale of 10 to the 5 to 10 to the 6 TeV, and we only need 10 to the minus 12, so m is roughly 10 to the 3 TeV, 1,000 TeV. Okay? Now, this is still an incredibly impressive number. You're probing 1,000 TeV. The LHC is roughly probing a TeV. Okay? And in fact, it's so impressive that you go to the ACME websites, they're at Chicago, Harvard, and Northwestern, and you find this. ACME 3 will be sensitive to new particles with a mass as high as 10 to 300 TeV, far beyond the direct reach of any high energy collider. Okay? So people start to get very territorial about what their tools are able to do. Okay? But at the same time, there's a very important lesson hiding in this in terms of our estimates. Okay? If we think that these estimates are exactly the God's honest truth, then we can kind of think of it in sort of like the tortoise and the hare version of all particle physics. Tabletop experiments are always going to be beating high energy colliders because it takes so darn long to build them. Okay? But if we reverse this logic and said, hey, the standard model EDM only showed up at 4 loops. All I've done so far is to take a tree level Wilson coefficient and get this ridiculous scale of 1,000,000 TeV. I did a Spurian estimate with the electron Yukawa, and I said, okay, now we're down to 1,000 TeV. Well, if I had something that had new CP violation directly coupled to the electron at tree level, lots of other bad things are going to happen. Okay? So if you typically look at new models with extra phases for CP violation, they show up at multi-loop order. They don't have to show up at 4-loop order, but for instance in supersymmetry, it shows up at 2-loop order. Okay? So then you can say the same sorts of games, and instead of having the scale be 1,000 TeV or a few hundred TeV, if you say that your EDM is some G BSM in terms of some coupling to the BSM physics over 16 pi squared to the number of loops, and then we still have to have a dimensionful scale, so we still should use our ME over M squared. And now what you get is that now M, if you did 2 loops, like in SUSY, this is roughly the TeV scale, what we're probing with accelerators. Okay? So there's an incredibly important lesson hiding in here about EFT and precision physics, okay, that doesn't often get stressed enough, because as tools, we often tend to think, I am a precision physicist, I will work on my tabletop experiment. I'm an accelerator physicist. I will work on my high energy experiment. Or I am a cosmologist. I will look up at the heavens. Okay? As theorists, though, we have to understand the interrelations of these things to understand when are we probing new territory or not. Okay? The problem with indirect evidence is that it is indirect. We haven't seen these new states. So therefore, if I think about the Acme experiment, which is a beautiful experiment, and the next generations are improving by orders of magnitude, these are absolutely directions that we need to pursue. But as you see here, we have 3 orders of magnitude in terms of realistic estimates for where it could be. So from our perspective, since the Acme experiment would never actually, even if they find an electric dipole moment, tell us what the physics is, we need to figure out whether we're living way out here or whether we're living next door. Okay? So the 2 perspectives from this are, 1, if it is at some astronomically high scale, we need to figure out what are the tools that we need to prepare to reach that scale eventually, okay, to be able to test it. The other perspective to think about is, even if it could be living here, if we see a non-zero electron EDM, it also could be living down here. And it could be living below where the Acme experiment is sensitive to. Okay? So in some sense, any indirect measurement, no matter how good it is, we're just setting essentially some line through this space of coupling versus masses. Okay? And so we need to be able to not only get to the place where it could be showing up, we need to test this entire space. Okay? We need to develop tools to go everywhere. Okay? Now, these sorts of arguments that I just used for the EDM, you can play these sorts of arguments for other precision experiments as well. So sometimes, sorry, was there a question? No. Sometimes collider experiments can be precision experiments as well.
Patrick?
Yep. Sure. That can be your job. Just tell me where to go. I'll just follow directions. There's many processes that are suppressed in the standard model for a reason or another. So for instance, other examples are so-called flavor changing neutral currents or custodial symmetry violation. Okay. So I didn't check whether these all came in the first lecture. When I was in TASI, these things came up in the first lecture. If not, just bug me in the coffee break. But basically, we can do the same sorts of arguments and say, well, if I make a KK bar mixing operator suppressed by some scale, well, this scale needs to be greater than around 10 to the 4 TeV. You can have similar ones with BB bar oscillations. This sets a scale about 10 to the 3 TeV. And if I do DD bar oscillations, sorry, that was 10 to the 4. This is 10 to the 3 for DD bar oscillations. And then if I write down a custodial symmetry violating operator like the T parameter, this tells me a scale roughly greater than 10 TeV. All of these experiments tell us that it's well above what the LHC would probe, so should we have ever turned the LHC on? Well, the nice thing about this is you can do the same sort of spurious arguments that we did over there and show that there's actually a wide range of scales, okay? So we shouldn't just focus all our efforts and put all our eggs in the precision basket. We need to also figure out how do we actually probe at the highest energies as well. And some questions that we'll get to on the third day are really purely suited for high energy, right? The Higgs mass wasn't discovered until the LHC. Yet the Higgs shows up in lots of standard model processes at loop level. The problem is, it's just the precision is not there to exactly pin it down. For instance, the G-2 experiment is absolutely beautiful. The bar Z diagrams of the Higgs, these come up, but you can't set the Higgs at 125 from the G-2 experiment, okay? So we need to think about, more generally, how do we actually go to high energies, and figure out the technologies that'll get us there. Okay.
I think for EVM we use kind of a naturalness argument to say that.
For the ME example, yeah.
So we have a safety here for these bounds.
So each of these bounds will have slightly different arguments in the sense of the reason why flavor changing neutral currents are so small in the standard model and why these scales turn out to be astronomical is that in the standard model there's the Jim mechanism, okay, which says the unitarity of the CKM matrix makes these things disappear, okay, and in loops they get suppressed by small couplings and the Jim suppression. This is just assuming this operator is turning on with order 1 coefficient and a mass scale. Okay? So even if you had new physics, you're still going to have some coupling constant, okay, which will reduce this scale. And then furthermore, you could have something like the Jim mechanism or some flavor symmetry that suppresses this. So it doesn't have to be a naturalness argument. It's just built into the structure of these things. So for instance, it's actually very easy to have new physics that affects flavor at the TeV scale, but has a very different flavor hierarchy than the standard model. This example of custodial symmetry violation, which I said 10 TeV, which is still above where the LHC is probing, well, if your new physics model has this custodial symmetry that the standard model has in the XNL symmetry, or you can be even more agnostic and say, hey, maybe I don't have custodial symmetry. Maybe I just have a weak coupling, and it comes up at loop level. If you stick a weak coupling in loop level with the mass scale here, now the scale is 100 GeV rather than 10 TeV. Okay? So it's different arguments in all these, but the point is indirect measurements, you're never going to know for sure. You always have more than just a mass scale in terms of the UV theory that your IR physics flows. So hopefully this is at least motivated that indirect is not sufficient to do everything, and we need to study these extra tools. And colliders have a great history of doing this for us as well. So Jesse snuck out before I was here, but so Jesse used this plot at the SNOMAS studies a couple years ago, and this comes from The Economist magazine. And this is a really great plot because it has what are all the particles of the standard model, when they were theorized, when they were discovered, okay? Jesse was using this from the theory perspective as saying, like, look, theorists were able to read the tea leaves and understand what should be there quite often before experiment. Sometimes you have complete accidents, like the muon, okay, the who ordered that particle, or the tau, okay? But theory often leads the way. But the reverse of this is even if theorists, we think that we're brilliant and we can do all these things, we actually have to discover all these particles. And so accelerator physics has actually a very great track record of discovering new particles and new states. So what I've done here, it's a good exercise historically to understand where all these different things were discovered. And what you see here is except for the muon for cosmic rays, and then the electron neutrino that was discovered using reactor neutrinos, okay? Every single particle that we've discovered has been due to accelerator physics, okay? So it's got a great track record so far. And the question is, how do we take this indispensable tool that we've used so far and keep pushing it further? So if we go back to this toy cartoon that everybody likes to use, whether you're talking about dark matter or Higgs physics in terms of coupling in mass space, since indirect bounds always kind of place a line here depending upon the precision, because we think of this as some EFT operator, we have some couplings and masses. What we can think about, though, is what happens if we just sit back and keep building more and more powerful accelerators, and could we eventually just cover everything, right? Maybe we can build the Planck scale collider, and we can cover every possibility that's around there. Now, the real question, which is where theory kind of meets experiment and meets accelerator physics, is understanding what are the prospects for actually doing this, okay? What technologies are available? What are the elementary forces we can use to make these sorts of experiments and to eventually cover this in principle? And we have all examples of this, whether in terms of talking about many of your AIML talks, this TOSI, or whether you talk about computing power. Technology is always getting better and better, okay? So we always have the kind of standard example in terms of computing power. We talk about Moore's law, but it turns out a long time ago there's something similar to Moore's law for accelerators. It's called Livingston's law. Okay? And what this represents is going back to the very first accelerators back in the 1920s or so. If you looked at the energy of the beams you can make in accelerators versus time, you also see a very strong growth. Okay? Now, the thing to keep in mind, though, is even if I can make some sort of power law that goes through this, and I can go and eventually hit the Planck scale, there's a lot of things written on this plot that are probably hard for you to read. All of these represent different sorts of accelerating technologies. So even though there's a growth, certain types of technologies fall off the growth curve, and new things have to come on. Yep.
I notice your x-axis ends in the late 50s.
Because this was when the plot was made.
So has this extrapolated?
I will show another version of this. If you do extrapolate, though, okay, and the extrapolation actually turns out to not be that bad from what this was, roughly 300 years from now, we can hit the Planck scale. If we can do it. So we're not going to do it, but it's not that far futuristic. I mean, 300 years is interesting. But the important part about this is to understand this very question. Do we hit a wall? Okay? Is there some fundamental technology limitations that says we're not going to keep this doubling of energy every 6 years as it goes on? Okay? But at the same time, thinking about this, it's not just kind of reserved only for crackpots that would imagine extrapolating 300 years in the future. So now we'll go back to the one old collider that Tom hadn't heard of, the Globaltron. Who came up with this idea? Well, nobody knew the answer, but you can guess. Who wants to guess who came up with the Globaltron?
Everyone at the same time.
There was a person, a very famous person. Definitely not. Fermi. Fermi came up with the idea of the Globaltron back in the 50s. Okay? Because they saw this extrapolation in the sense of collider technology. Well, there's going to be a limit in terms of how much the technology can push versus how do we have to go bigger and bigger and bigger. Okay? So the idea behind the Globaltron was, well, we're just going to make a ring to go around the entire world. This has now been kind of modified. There's other crazy versions of this idea. One is called Collider on the Moon. Frank Zimmerman, an accelerator physicist at CERN, put that out a few years ago. And then there is actually a very interesting one called Collider in the Sea, where you could build essentially a 500 TV collider in the Gulf of Mexico. I'll tell you why that's interesting at another point. But the point is, if Fermi can dream big like this, all of us can feel the license to dream big like this as well. Okay, we can say, oh, Fermi did it. We can think about this as well. Now, an interesting thing, though, in terms of the graph for the Livingston's law that we had here and this Globaltron, sometimes technological developments seem absolutely trivial in retrospect, but they are very difficult. This Globaltron was not actually a collider. This Globaltron was a fixed target experiment. So the bounds on this Livingston law, this is the energy of the beam, not the center of mass energy of a collision. This is just the energy of the beam. And now, as like any first-year undergrad, the first or high school, whenever you talk about special relativity, we know that there's a fundamental difference between talking about fixed target experiments versus collider experiments. Okay? So if we just ask, what's the difference between the two in terms of I have some form momentum coming in, hitting some fixed target particle at rest? Well, we say that if this is my P1, this is my P2. Well, if I want to calculate the center of mass energy, I look at the Mandel-Stamets variable, where we have P1 plus P2 squared. So this one, we'll assume it's relativistic. So we'll have some E and P, and then we'll have a m comma 0 for our at-rest target. And we know that this gives me roughly 2e times the mass of the target. Okay? Now, if we do the simple thing of saying I have a collider experiment, okay, as theorists you'd say, oh, this is completely obvious if I take this and I make them both moving so that I have my P1 now has some EP and my P2 has some E minus P. And then you go through and calculate, and you say, well, my S now is 4E squared. Okay? Now we do the simple sort of estimates and say, okay, the center of mass energy will be the square root of 2em versus ECM in a collider experiment will be equal to 2e. And now let's play the game of the LHC for a second. Okay? At the LHC is roughly a center of mass collision at 14 TeV, okay, which I'll use as 10 in this estimate because I don't want to do any harder arithmetic. And we know the LHC collides two proton beams that each have an E beam of 7 TeV. If we wanted to do a fixed target experiment that achieved the same center of mass energy of the LHC, well, what we'd have here is then we'd have something that's of order 10 TeV had to be about the same as the energy of the beam times 1 GeV, the mass of the proton. Okay? Now, since I have to take the square root with the GeV, well, what we get out of this is that E beam for a fixed target experiment to do the exact same physics as the LHC comes out to be 100,000 TeV. Okay? Astronomically beyond any technology anybody has even proposed. Putting a collider on a moon doesn't even do this for you. Okay? But what this shows is that sometimes something that's very simple from the theory point of view, right? Anybody can do this sort of simple exercise once they learn special relativity and kinematics. It actually has these huge, many, many orders of magnitude implications in terms of what it does for accelerator technology. And so the reason why Fermi, even though he was future thinking enough to put an accelerator around the Earth, it seemed absolutely insane to him that you could take two particles, accelerate them both, and somehow find each other with that level of precision to create a center of mass energy collision. Okay? So these are the kinds of things that, as a theorist, you might say, oh, obviously you would do this in retrospect. But in terms of the technology that we have to apply to be able to make a collider, okay? A collider in some sense is the pinnacle of physics technology achievement in terms of if you wanted to make an experiment like this. So we need to really understand how do we figure out what the limitations are. So after this very long-winded appreciate accelerators intro, thank you. What I want to do is set the stage for what we'll talk about tomorrow, where we actually talk about the technology of accelerators. Okay, what goes into it, what's plausible, what's not plausible. Now, the starting point, though, before I even talk about how you make an accelerator, what are the technologies we use, I mean, you can remember these names for tomorrow if you want to ask. I'll go through some of these. The real question, though, is even if I make some magical machine that could accelerate to 100,000 TeV, okay, how do I get the physics out of it? Now, for the half to 2/3 of the room that have done collider pheno projects, you already understand how this works, but there is still a little bit more than what we typically do in a collider physics project. So for instance, in every quantum field theory intro book that you see, whether it's Peskin-Schroeder, Schwartz, Srednicki, whatever your favorite one is, we typically always see a starting point which is define a cross-section in particle physics. Okay? And the way we deal in most all intro textbooks is to start with some notion of a classical cross-section and try to come up with a definition of a quantum mechanical cross-section. And it typically goes in one of a variety of ways, but the starting point from the classical side is to say, hey, I have some flux of particles that hit something and scatter off in many directions. Okay, and that's how I define my classical version of cross-section. And then what I have to do is somehow take this to the quantum regime. And that typically follows the steps of saying, I get to a quantum mechanical version of a cross-section from going from a classical cross-section, turning into quantum mechanical one through the S matrix. And then we do the next step, which is we apply the LSZ formula, and then we get to some time-ordered correlation function of our fields involved, where this would be some cross-section of a 2 to n process. Okay. So everybody sees something like this at some level in your interquantum field theory. Okay. Now, if you go to Stony Brook, we have a weird system where Sasha Zamolodchikov teaches the first part of the course, and even though he is one of the unparalleled masters of quantum field theory, he never shows this part. Hep-TH people only care about correlation functions. Some care about S matrices. Most of them do not care about cross-sections ever. Nonetheless, if we get through that whole rigmarole and define a cross-section, then the next thing is, well, we define the classical cross-section through this notion of a flux on some target. The next thing we do is we say that the number of events as a function of time, I can call this the differential number of events, is something given by the luminosity of the particles times the differential cross-section. Okay? And then you integrate it and you go along your merry way and you say, quantum mechanically, I'll get this number of events if I have some integrated luminosity times the cross-section. Okay. And we go off, and if you do a pheno project, that's kind of the 0th order thing to say, do I have enough events? And then you have to go a little bit further. Okay. Now, of course, that's great for theorists. And if you're not a collider phenomenologist, that's where you stop normally. But these are the events that come out. This is a Higgs to 4 electron event at the LHC. So obviously, one number doesn't classify that event sufficiently. And we have to go a little bit further. So the next thing you do is if in your collider pheno studies, you say, well, I can calculate my differential cross-section, or I can do a Monte Carlo evaluation of the cross-section and generate events to look like that. And then we say something like the number of events looks like my integrated luminosity times my cross-section, and then I'll have to fold in some efficiency and acceptance for actually detecting the particles. Okay? Because even as theorists, we'd like to say we can make inclusive things, but experiments always like exclusive things typically. And then last but not least, this is the number of events for a signal that we're interested. We also have to have some number of background events because quantum mechanics doesn't say, hey, I'm a Higgs boson. It comes down the particles we know, so we have to interpret this. Now, this whole story, there are many different tools to do this, right? Each one of these kind of set of tools is its own set of TASI lectures in terms of if you want to calculate these cross-sections at sufficient precision, we have to be able to go to higher orders. Those are more lectures. If you want to calculate the details of the efficiency acceptances, this is detector design. This is signal modeling. You can use AML techniques to separate signal from background. And often, all of our physics as collider pheno people go in this direction. We still aren't thinking about our accelerator friends too much. The accelerator physicists are just setting the machine parameters. They say, hey, we'll give you this much luminosity, and we'll tell you what the incoming momentum and energy of these particles are. Okay? So for instance, at the LHC, the parameters that we typically stop caring about after talking to the accelerator physicists are the integrated luminosity for the high luminosity LHC is 3 inverse attobarns, and the center of mass energy is roughly 14 TeV. Okay? That's normally how much we care about accelerator physicists. Okay? Now, what I'm here to tell you over the next 2 days is that's absolutely wrong. I made this mistake. I don't want you all to make the mistake. There's actually secretly a lot of physics here that actually determines everything that we can get out up here in terms of those events. Okay? So if we take these two numbers of integrated luminosity and cross-section that were just handed by some accelerator physicists, let's go through the first kind of iteration on what matters a little bit more. So if you're a collider physicist, you say, Now I plug in what my cross section is with this luminosity. You say, I can see something or not, or I can do this precision or not based on the number of events that I can see. But at the same time, the idea of searches, precision, or just kind of regular vanilla standard model physics and testing it, this all is linked in the sense that whenever I have an integrated luminosity, for instance, 3 inverse Aldebarans, from the equation I erased, remember, this is some instantaneous luminosity times time that I'm going to run my experiment for. So before we finish up, let me give one more question for all you. Does anybody know what the rough instantaneous luminosity of the LHC is? For those who did collider projects, can you give me like an order of magnitude? I'll let you pick your unit. Okay, I'll just write it down for now. So the instantaneous luminosity of the LHC is roughly 10 to the 34 inverse centimeters squared per second. Okay? That's some number. Seems to be obscure. You care about what the integrated luminosity is, so you can multiply by your cross section and tell me how many events there are. But there's actually a lot of physics hiding in that. Okay? Yep.
Is that number before or after the trigger?
This is before. The luminosity doesn't depend on the trigger. This is just what's in the beam. So from that perspective, you can think of the trigger as putting this efficiency acceptance on there. So if I have that number, though, that number sets a lot. All right? This 3 inverse Aldebaran number says I can probe roughly Aldebaran physics at the LHC, and I can do precision on cross sections that are larger than an Aldebaran. However, if I take this 10 to the 34 inverse centimeters squared per second and say, what does that tell me? Well, an inverse Aldebaran, in terms of getting integrated luminosity, this is 10 to the 42 centimeters to the minus 2. Okay? So what you see here is that if I want to do physics with this kind of scale of integrated luminosity, and this is what an inverse Aldebaran really is, the instantaneous luminosity really sets the lifetime of what you're going to do as a physicist, okay, if you want to do any collider physics projects. So I need to make up 8 orders of magnitude to get to an inverse Aldebaran with that instantaneous luminosity. That means I need a time of order 10 to the 8 seconds. A year is roughly 10 to the 7 seconds. So immediately, if I want to probe 3 inverse Aldebaran physics, what this tells you is the experimental time now has shifted to roughly 10 years. And that's assuming that you can run every single second. Okay? So this gives you just kind of a very simple estimate to understand the LHC turned on just roughly before 2010 in terms of timescales. It's going to run till roughly 2040. This is a 30-year experiment. Okay? It's not a 30-year experiment because everybody wants to do the same experiment for 30 years. The 30 years is set by this collider physics parameter. Okay? So one thing that you need to ask yourself is, well, can I get a better instantaneous luminosity? Could I do all the LHC physics in 3 years? Even if I couldn't accelerate to higher energies, could I get it done faster by increasing the luminosity? Now, from the particle physics perspective, this is some crazy number in terms of centimeters squared per second. Is there any fundamental limitations? Okay? And so we need to figure out whether this is going to turn us into multi-generational physicists that have to wait 100 or 1,000 years to reach your cross sections you want, or whether you can do this on a time scale that matters. So the other side of this is, let me just take 2 more minutes to do one quick last estimate. This is the LHC right now. What we also know is that if I take any physics process, whether it's supersymmetry, whatever your BSM physics, axions, whatever you do, if I need to use high energy to probe it, using some standard model particles and some BSM states here. Right? This is scaling as 1 over s for an S-channel process. Okay? And so roughly at the LHC, we have scales that are roughly 1 over 1 TeV. Okay? That's the rough scale that we're probing on average with the LHC. Now, if you put 1 over TeV squared into this, that tells us that the cross-section is, if we convert the units, our cross-section is 10 to the minus 34 centimeters squared. Not surprisingly, this is a very well-fit number for probing the TeV scale. Okay? We're roughly producing events a second at order TeV scale. But now let's say you wanted to build a higher energy collider. Let's say we want to go an order of magnitude beyond where the LHC is. Well, quantum mechanics tells you that regardless of what your amplitude is, in the S channel it always scales like 1 over s. So if I was to do this, and now I put 1 over 10 TeV squared, okay? Now we've generated 2 more orders of magnitude, okay, in terms of the energy scale.